So it starts at 0 here, x equals 0, and it goes all the way out this way to infinity. Just keeps going forever. So this one's a type 2 improper integral because it's got a vertical asymptote here at 0, and it's a type 1 improper integral because it's going all the way out to infinity here. So what we could do with this one is divide it into 2 parts. I'm just going to divide it at 1, but you could divide it anywhere you want, anywhere, any positive number. Okay, so that's this part here will be our type 2 improper integral. And whoops. This will be our type 1. So this right here is equal to the integral from 0 to 1 of 1 over root x times x plus 1 dx plus the integral from 1 to infinity of 1 over the root of x times 1 plus x dx. So that's the first one, and this is the second one. But as I say, 1, I just chose that 1 arbitrarily. You could have divided it at any positive number. Now, yesterday I showed you how you can find the antiderivative. The way it's written with the root x could easily have been distributed over the x plus 1. But the way it was written with it not distributed is sort of a hint, because remember, d by dx of root x equals d by dx of x to the 1/2 equals 1/2 x to the minus 1/2 equals 1/2 times 1 over root x. So you've got this 1 over root x here, which you could use as a du. You've got 1 over root x dx, which could be used as a du. And that means if you could let u equal root x. Well, if u equals root x, then u squared just equals x. So the thing becomes 1/2 the integral of 1 over x squared, or sorry, u squared plus 1 du. And so this 1/2 du is the, oh sorry, it's not 1/2, I beg your pardon. Du equals 1/2 x to the minus 1/2. So you'd multiply both sides of this thing here by 2, and you get 2 du equals 1 over the root of x dx. So this is going to be a 2. And then the u squared is going to replace the x. So this is kind of a different, sort of a tricky substitution. But of course, now that you've got the substitution, you can see it's just going to equal to 2 times arc tan u. And u equals the root of x, so it equals 2 times arc tan the root of x. So that's our antiderivative, capital F of x. Okay, so the first part, the type 2 one, the yellow part, is going to be the limit. Remember, the problem here is at 0 in this part, because there's a vertical asymptote at 0 here, right? So that's the thing you're going to replace with say, well, B or A or something. We'll call that B. And we're going to take the integral from B to 1, and then we'll do that, and then at the end we'll take the limit as B approaches 0 from the positive side, because you can see B is going to 0, right? If B goes to 0, then that gives you the whole thing. So the limit as B approaches 0 from the right, the integral, and the 0, that's where the problem is. So that's the one that gets replaced with B. From B to 1 over root x onto x plus 1 dx. And then the second part is going to be the integral from 1, well, to infinity, but I guess we need to put a limit on that one too. So what here we'll do, we'll call this, say, t. And we'll take the integral from 1 to t, and then we'll take the limit as t approaches infinity. So we replaced infinity with t, but then we have to put this limit as t approaching infinity. Here we replaced 0 with b, so we have to take the limit as b approaches 0. Okay, so we've got the antiderivative as 2 arctan root x. So this is going to be the limit as b goes to 0 on the plus side of 2 arctan root x taken from b to 1 plus the limit as t goes to infinity of 2 arctan root x taken from 1 to t. Okay. So this one will give us the area that's colored in yellow, and this will give us the area that's colored in turquoise, or whatever that is. So if we add them up, we get the total thing. Okay, so 2 arctan, the root of 1, minus 2 arctan, the root of b, plus limit as t approaches infinity of 2 arctan, the root of t, minus 2 arctan, the root of 1. Okay, so the root of 1 is just 1, and the arctan of 1, well, you can do that on your calculator. Make sure you're in radian mode. You might remember it's the angle whose tangent is 1, and you get a tangent of 1 when you're in a isosceles right triangle like this. 1, 1, root 2, and then these are 45 degrees, right? Because it's isosceles. And 45 degrees equals pi over 4 radians. So the tangent of pi over 4 radians equals 1. So that means the arctan of 1 equals pi over 4. So, and then let's see, if we take the limit here as b goes to 0, well, that's just going to give us the arctan of 0, which is just 0. So this is just going to go to 0. So this is going to be 2 pi over 4 plus 0 plus, and again, this part here is going to be 2 pi over 4. But remember, we saw this an example like this yesterday, where we had the limit as t goes to infinity of arctan t. Well, as t goes to infinity, the root of t is also going to infinity. And remember, we saw this yesterday, that if when t goes to infinity, arctan of t goes to pi over 2. And you can make a little table if you're not sure. And even if you didn't recognize that it was pi, like, well, this is 2 times the arctan, so it's going to pi. But even if you didn't recognize that, you know, you could always just put in a decimal approximation. So this is going to 2 pi over 2 minus 2 pi over 4. So I guess these parts are just going to cancel. And you're going to be left with just pi. Or approximately 3.14. So that's the area. I think I just picked this one because it's sort of interesting that when you get something like that and it has an area of pi under it. It goes to infinity in both directions, up this way and up this way. Okay, so any questions about that one? Okay, I gave out that worksheet on improper integrals yesterday. You didn't, and also on approximate integration, the midpoint of the trapezoid rule. There's some here if you want to pick one out. There's also another worksheet on Moodle. Okay, so that brings us to a new topic. I think from this point on, we're doing applications of integration. And from this point on, the integrals get easier. Because when we're doing, up until now, we've sort of been learning new methods of integrating. But we're not going to learn any more new methods. We've done with that. We've got all the methods we need now. And we're going to look at some applications. So if you're doing an application, I mean, occasionally you might run into an integration by part or something, but we won't see much of it. Okay, so the first application is finding area between curves. So the area of a region bounded by the curve f of x and g of x, and the lines x equals a and x equals b, where f and g are continuous, and f is greater than g. Let me just draw a little picture of this. Let's say this is f. So we have f greater than g. So we could make that one G maybe down here. And then we've got an A and a B. And what we want is the area between the curves. So we're trying to get this area in here. And here it says it's the integral of just f minus g. And the reason it works is because you take the integral from a to b of f of x dx. That's going to give you, well, it's going to give you this area here, right? The whole thing, all the way down to the x-axis. Well, in this case, f and g are both positive. But it turns out it works even if they're not both positive. Right? And then the integral from a to b of g of x dx is going to give you this part under here. So if we subtract the smaller one from the bigger one, then it just gives us a leftover part. So you're subtracting this away, this part under here, because that's the integral from a to b of g of x dx. And you just get the part that's left behind. And of course, you can write this as the integral from a to b of f of x minus g of x, because we have that nice convenient thing where the integral of a sum or difference is the sum or difference of the integrals, which of course doesn't work for multiplying and dividing functions. Okay, so let's look at this first example here. In this one, we can actually do it by geometry to verify the result. So f is one half x plus 3. It's just a straight line right here. And g is minus 1/2 x plus 3. So it's this down here. So let's just, well, first of all, we'll just do the integral from 0 to 10. Okay, from 0 to 10. So from 0 to 10. That sort of got left out a little bit. 0 to x equals 0 to x equals 10. It sort of got, the 10 part got sort of orphaned on the line below. So that's going to be the integral from 0 to 10 of 1/2 x plus 3 minus 1/2 x plus 3 dx. Now if it's got any like terms there, you can of course simplify them. So that's 1/2, you distribute this minus sign and you get 1/2 x plus 1/2 x plus 3 minus 3 dx. So 1/2 x plus 1/2 x, of course, is just x. Well, I told you the integrals get easier. Usually they don't get quite that easy. So the integral of x dx, well, that's just, you know, it's x to the 1, of course. So we just use the backwards power rule, right? So this is just x squared, 1/2 x squared, taken from 0 to 10, equals 1/2 10 squared minus 1/2 0 squared. Which is just equal to 50. So the area we're going after is this area here. And notice that G is negative on part of it. But remember, we're subtracting G. And when we're subtracting the integral of G, and when you subtract a negative, you get a positive. So in this case, in fact, we'd want to be adding that, and that's exactly what happens when you use the formula F minus G. So this part here would get subtracted with the G, and this part would get added, which is just exactly what we want. And you can just do it by geometry, using geometry. Because they're straight lines. So the base here is 10 of this triangle, and the height is 10. So it's just 1/2 base times height equals 1/2 10 times 10 equals 50. Which of course is what we got doing it the other way. Okay, so any questions about that? Let's look at another example. Typically, with these type of things, you'll get them intersecting. I always like to give you the graph, but if you didn't have the graph, you might have to find out where they're intersecting to find out what the graph looked like. But I'll always give you the graph. So it says find the area bounded by the graphs of f of x equals 4 minus x squared and g of x equals x squared minus 2x. Now you might not be sure which function is which. So you could say substitute as x equals 0 in there, and if we go into the formula, f of 0 is going to equal 4 minus x squared, 4 minus 0 squared equals 4. So this one must be f right here. And if you looked at g, you'd get g of g of 0, well, g is x squared minus 2x, so it's going to be 0 squared minus 2, 0 equals 0. So this one goes right through 0, 0. That one must be g. Okay, now we can see on the graph that they seem to intersect at -1 and at 2. But if you weren't sure where they intersect, I'll just show you this one time. To find where they intersect, solve, f of x equals g of x. So in this case, that would be 4 minus x squared equals x squared minus 2x. So it looks like it's going to be a quadratic function, so we could add x squared to both sides. and subtract 4 from both sides. And that would give us 0 equals 2x squared minus 2x minus 4. Now we could factor a 2 out of that to make it easier to factor. And let's see if that factors. X plus 1, x minus 2, that'll work. And if you set all those factors to 0, you get, well, of course, setting 2 equals 0 doesn't give you a solution. And this gives you x equals minus 1, and x minus 2 equals 0 gives you x equals 2. So anyways, you won't have to do that as a rule, because I like to give you the solution. I like to give the graphs. Figure that way, if you know, people who don't have graphing calculators, it just sort of levels the playing field. Make this a little bit smaller. Okay, so it's going to be the integral from minus 1 to 2 of f of x minus g of x. So that's going to be 4 minus x squared minus x squared minus 2x dx. So we have to apply that minus sign to everything in the second function. So it's going to be 4 minus 2x squared plus 2x. Okay, so the antiderivative is going to be 4x minus 2/3 x cubed plus x squared. Sometimes the hardest part of doing these is sort of the fiddly part at the end where you have to evaluate it. I mean, this one's not too bad, but it can get pretty weird. Two. That's the antiderivative at 2 minus the antiderivative at minus 1. Okay, so that's 8 minus 16 over 3 plus 4. Okay, so this is going to be minus 4, so minus 4 is plus 4. And here, when you cube minus 1, it stays minus. So this is a minus minus minus, so this is going to be minus 2/3. And then when you square minus 1, it becomes plus 1, so it's minus plus 1, so it's minus 1. So what does that come to? 8 plus 8 is 16, minus 1 is 15. So it's 15 minus 18 over 3 equals 15 minus 6 equals 9. Now you can look at the diagram to sort of see if it seems plausible. Well, in this case, let's see, where's this? Yeah, it's a different scale on the x and, oh no, it's not, it's the same. So that is, well, each of these little rectangular blocks is 1/2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah, so it seems plausible. Well, half of 15 would be 7.5, but I don't know. Doesn't seem too far off. Unless I made a mistake. Anybody get a different answer? When you got these fiddly parts at the end like this, it's always tempting to put it into Maple or into this calculator, this TI Inspire CX. It can do computer algebra. It can just do you just have to punch it in and it can do it for you. Okay. So the next one, we've got the sine and cosine curves. They intersect infinitely many times. Bounding regions of equal area. And we want to find the area of one of these regions. So if you're not sure which is which, remember sine 0 equals 0 and cosine 0 equals 1. You can do that on your calculator. Remember to be in radian mode, though in this case 0 won't matter. So this one here must be the cosine. I should go through this and make all the graphs in color. When I first made most of these notes, and this one here is the sine x, I was using overhead transparencies and it was too expensive to make them in color, but now everything can be in color. So we need to, now again, I would probably give you the intersection points because it's kind of a pain finding them. But they intersect, of course, where sine x equals cos x. Right. And to solve that, you could just come along and divide both sides by cos x. And that tells you that, well, what's sine x over cos x? We're on, what do we call that? Yeah, that's the tangent of x. And cos x over cos x is 1. So that means x is going to equal the arc sine of 1. And remember, we were just talking about that on the other page, and this is pi over 4. But if you just get a decimal for it, that's okay too. And the other one is going to be well, let's see, this is pi over 2. This is pi here. This is 2 pi. That's one complete cycle. So this must be 3 pi over 2, or 1.5 pi. So this must be a pi plus 1/4 of a pi. So in other words, it's 4 quarters plus 1/4 would be 5 pi over 4. But I will, like on a test or something, I'll give you where they intersect, especially if it involves solving a trig equation, which are always kind of a pain in the neck. Okay, so all we have to do is integrate from pi over 4. I'll make the graph so that it's in terms of, it's got multiples of pi along the axis instead of just numbers. So this is going to be the sine minus the cosine. Because you always got to take the one on the top minus the one below. If you ever get a negative number, you know you've done something wrong, because you should always get a positive number. So the antiderivative of sine is negative cosine, right? And the antiderivative of cosine is sine. So this is going to be negative cosine minus sine, because the antiderivative of cosine is positive sine, taken from pi over 4 to 5 pi over 4. And again, these fiddly parts at the end actually, this is where, yeah. Minus sine pi over 4 minus cosine 5 pi over 4 minus sine 5 pi over 4. Well, sorry. Oh, sorry. These ones should just be pi over 4. Okay. So the cosine of 5 pi over 4 is, I believe, minus 1 over root 2. But you can just do it on your calculator. Well, mine's actually giving me, well, it's giving me root 2 over 2, but it's minus 1 over root 2. But you can just do it as a decimal if you want. Like it's minus 0.707. So we might as well just do that. And the sine is the same, because we can see at that point the cosine and sine are both the same, right? Okay, and then minus and minus is going to be a plus, and then the cosine of pi over 4 is plus 0.707. And then minus a minus is a plus 0.707. So this is minus a minus, so we get 4 times 0.707, or 4 times 1 over root 2, and that comes to well, it comes to about, oh, a second. Yeah, it comes to about 2.828. Which is 2 root 2. Did anybody get a different answer? Each of those rectangular blocks is area 1, so seems sort of plausible. 2, 1 bit. So we'll continue with this tomorrow.